Okay, in this last lecture of design with using frequency domain methods, or in particular the Bode plot, we will look at designing both lead and lag compensators. So just to again recap what we did earlier was, so you have this region 1, which was a low frequency region where we want the gain to be as high as possible so that we have low steady state errors. In the region 2, it should have some satisfactory gain and phase margin. So this corresponds to the transient region, the steady state region, and the high frequency region. Okay, so what is this lead-lag compensator all about? So if we remember what we had done while we were doing the design with root locus methods, we had a component which was essentially a lead component and a lag component, and of course taking care of all the lead and lag components, and beta should be 1 for something greater than 1, and alpha and beta here are 1 if we directly map to what we had done in terms of that one. So alpha times beta is 1. So I have a lead and the lag components, and essentially I am now looking at designing this compensator with a gain k prime, and GC is again split into the gain component and then the dynamic component. So something like this. So as usual in the design process, we design the gain k prime first and then go about designing this one. Okay, so let's see how the frequency response or the frequency characteristic of this lead-lag compensator looks like. So if I just draw the Bode, so what I see is, well, I have the lag component here and then the lead component. You could also see it with the with the magnitude plot, right? So this corresponds to my lag, where you will have attenuation at higher at these frequencies, for example, and you will also have this to be the lead component. Okay, so what we observe here is, of course, these are my corner frequencies 1, 2, 3, and 4, and these 4 corner frequencies will decide how my design of the compensator look like, or how the poles and zeros of my compensator are placed. Now if I look at the phase plot, there is a certain frequency over here at which the angle goes to 0. Now what is this angle? This angle, the frequency at which the phase angle is 0, if I call this as omega 1, the frequency at which the phase angle is 0 is this one. Okay, now how do we compute this? Now what are this T1 and T2? This T1 and T2 essentially come from here. So T1 corresponds to this part of the compensator, T2 corresponds to this part of the compensator. Okay. Now, okay, so how do we do this? So I'll just quickly run you through the proof. So you have the angle of GC j omega is, so you have the angle of j omega plus 1 over T1. Similarly, you have the angle j omega T2, and now the angle of the poles with a negative sign, j omega beta over T1, j omega plus beta T2. This could also be written as the tan inverse of omega T1, tan inverse of omega T2 minus tan inverse of omega T1 over beta plus tan inverse of omega T2 times beta. So I'll just split these two quantities, this guy and this one, and I just use a simple formula which we learn in trigonometry. So tan of A plus B is tan A plus tan B over 1 minus tan A, then then the tangent of B. So, if I take the tangent of this entire guy, what will I be left with is I have omega t1 omega t2 over 1 minus omega t1 omega t2. Similarly, on this side I will have omega t1 over beta plus omega t2 times beta over 1 minus omega t1 and omega t2. Okay. Now, what happens when this is true, right? When omega 1, or at a frequency where omega 1 is 1 over square root t1 times t2, I substitute it over here, and I see that the denominator tends to 0, denominator tends to 0 here also. Okay, so what I will be left with is, okay, so the tan of this entire first term is infinity. If I take the inverse tan, what I get is that whatever is remaining inside has an angle of pi over 2. Similarly here, right. So, the tangent of these two terms added up would be infinity, therefore, whatever terms in the bracket is pi by 2. So, I have a pi by 2, and this happens only when at these frequencies, right. I am looking at a situation where omega is 1 over square root of t1 times t2, and at this frequency I get, if I substitute this here, I get a pi by 2 minus pi by 2, and therefore, the angle contribution, the angle of GC of j omega at this frequency, omega is 1 over square root t1 t2 is actually 0. Okay, so just a little summary of what we learned so far. So, if I look at a lead compensation, well, as the name suggests, it provides a phase lead, which means it improves the stability margins. It also has a higher gain crossover frequency, which means it has a higher bandwidth, and we know what is the relation now between bandwidth and the damping ratio, and that suggests that higher the bandwidth, which would mean lesser settling time. And of course, it needs an additional gain, increase in gain to offset the attenuation. The alpha was less than 1, therefore, we had to put some kind of a gain there so as to offset this attenuation. Okay, so the lag compensator, it reduces the system gain at higher frequencies in such a way that it does not affect the system gain at lower frequencies. So, only the higher frequencies are attenuated. Reduced bandwidth obviously means lower response, and it helps in steady state accuracy, right, as we see also in the time domain. Because of this property of reducing the system gain at higher frequencies, it helps attenuating the high frequency noise. And another drawback was, well, this pole 0 combination near the origin. So, the compensator poles and zeros in the lag case are placed very close to the origin, and this will lead some kind of variation in the transient response in terms of the settling times. It will have a long tail with small amplitude in the transient response. Okay, so now if both fast responses and good static accuracy are desired, then you go for a lead-lag compensation. Increase in the low frequency gain would mean improving steady state accuracy, and of course, the bandwidth and stability margins can also be increased when we do the lead and the lag design together. Okay, so let's start with an example to see what I am trying to say here, that I am given a transfer function which looks like this, and it is desired that kV is 30. Okay, if I write down the units, it is per second, phase margin is greater than 50 degrees, and the bandwidth a certain number of 12 radians per second. Okay, so what I will do here is I will try to solve this in MATLAB. I just plot everything for you, and we will see how the design process goes. Many times while designing, I had mentioned that, well, the design is not a one-step process. You may have to do it over and over until you reach closer to the solution. So in the first iteration you may be close to the desired results, but not. Then maybe in the second iteration you may tune your parameters, which are essentially the beta. Maybe you can choose a different alpha and beta, as we did in the time domain analysis, to just tweak it a little bit so that you get the desired response. So I'll just quickly run you through that process of going about that. Okay, so before that, right, so we are given this kV. Now kV should be 30 seconds. So what is the kV in my case? kV in my case is the standard formula, limit s tends to 0, s times g of s, that becomes k here. So for kV to be 30, this guy k should also be 30. So I am looking at a gain compensated transfer function, or the plant also, right, the gain compensated plant, which now looks like this as 30, and the rest of them is the same. I have a j omega, 0.1 j omega plus 1 and 0.2 j omega plus 1. Okay. Now let's go to MATLAB and try to see what this gain means in terms of stability margins. So I have G as $30, and here I will have 0.02, 0.3, 1 and 0, like a transfer function 30, 0.02 s cube, 0.03 s square and s. This is the transfer function for this guy. Okay, so if I do the Bode plot of this to see what does the gain compensation do to me. Okay, so I have the plot here. Okay, so I'll see via the grid the characteristic all stability margins. Okay, so I have phase margin of -17, a negative gain margin, and it shows that the closed loop system is unstable. Okay, so something not very good has happened here. So, and also if I look at what is the bandwidth, so at what time am I reaching -3? So look at this, go here, so roughly about 11, something about 11 point what is it? Oops, it's about 11.3 radians per second. Okay, so let's just note that down. So the gain compensated system has, well, this is unstable. It has a negative phase margin, a negative gain margin, and also it has a bandwidth of well, roughly about 11 radians per second. Okay, so this bandwidth is what I measure looking at the open loop Bode plot with a gain k of 30. So the specifications are usually in terms of the closed loop bandwidth, and in the previous lectures we saw how closed loop was in a way related to zeta with some kind of complicated formula. Okay, so this bandwidth of 11.8 radians per second is for the open loop. How does the closed loop bandwidth look like? Well, typically the closed loop bandwidth is, if I say denote this as the closed loop, it is usually greater than the bandwidth for the open loop. So if this is 11 here, the closed loop bandwidth would be roughly about 13. So we can check this with the help of the closed loop Bode plot, or if we were to do the design through the design process, check the bandwidth, we may have to use complicated plots like the Nichols chart, but we will try to avoid those. So what we will here do is, I mean, time and again we'll measure the open loop bandwidth, and typically the closed loop would be about about 20% higher than the open loop. Okay, there is no reason for me to say 20%, but I'll just make sure that my design for the open loop is around maybe 9 or 10, so that the closed loop is close to 12, right? So this we may have to check. You may take the Bode plot for the closed loop system and see that the bandwidth for the closed loop system is actually 13 radians per second. However, this is not very useful to us because I am just here dealing with an unstable system. Now let's just try what happens with just using a lag compensator. I'll just write down the steps here. Let me just take arbitrarily any. Okay, let's start with say a lead compensator. A lead compensator, so let me say it looks this form: j omega into 0.25 over 1 plus j omega multiplied by 0.025. I take a very liberal alpha which gives a very big phase lead of say 0.1. Okay, so now let's see what happens with this lead compensation. So there is no basis for me to choose this, but just to see a basic analysis what it is. So this is my GC1, I'll call it, is has a transfer function. So it has 0.25, 1, 0.025 and 1. Okay, so this is how my compensator looks like. Okay, so now if I do the Bode plot of G with GC1, which is my lead compensator, well, I get something like this. Okay. Okay, I see I have some improvement in the phase margin. The good thing is that the closed loop system is stable. It has a phase margin of 10, a gain margin of about 3.5 dB. Well, not bad, because at least I could get the system close to stability. And the bandwidth, if I go back, bandwidth of close to 20, okay, roughly about 20, right? Okay, so let's just note this down. Okay, so just by using a lead compensator, what I achieve is, well, the closed loop system is stable. Okay, now what is the phase margin? The phase margin is about, what was that? Phase margin was about 10 degrees and bandwidth was fairly large, 20 radians per second. Okay, so what is good? Well, this is good. This is a good thing, but it is far from desired. Desired was more than 50. So this is just about designing with the lead compensator. Let me just do with the help of a lag compensator. Right, and just take some standard this one, some standard compensator. Let's say it could be like 1 plus j omega 10 and 1 plus j omega 100. Okay, so let's see what MATLAB says because of this. Okay, so let me call this GC2. So I have 10 j omega plus 1, 101. Okay, now if I do the Bode plot of this plant with the lag compensator, and it looks something like this. Okay, there it is. and I am looking at the stability margins. Okay, so I see that my phase margin is quite good now. It's 42, a good enough gain margin. Let's say what is happening to the bandwidth. Where am I at? Minus 3 dB is roughly about 3.4 radians per second. So with this, my phase margin has shown some improvement. Well, the closed loop system is stable, which is good. Okay, my phase margin has become almost like more than 46 degrees. Then I have the bandwidth is 3.3 something like close to 3.4 radians per second. Okay, so let's now compare these two scenarios. So if I look at the lead compensator, the good thing was, well, the closed loop system was stable. Phase margin is 10. Earlier with the gain compensated system of k equal to 30, my system was unstable. Now it is at least stable. The bandwidth is 20. So this again I am measuring for the open loop. And if I just measure for the closed loop bandwidth is about 26 radians per second, and this thing is too large, right? And then the design specification in the previous slide here was in terms of the closed loop specification. So this is too large, and therefore it will be sensitive to noise. Okay, now this is about the lead part of it. Now what does the lag compensator do? Well, good thing is the system is again stable. Phase margin is close to the desired, it's 46.2, and what we want is about 50. Now the bandwidth is 3.34. This is again for the open loop. The closed loop would be about 4 radians per second or even less, and you see this is like far from desired. Right. So here I am not really computing this, but I will just use the open loop bandwidth as an indication of what is happening in the closed loop system. So comparing these two, I see that well, I have stability in both cases. Phase margin is good, but the bandwidth is too large. On the right hand side for the lag compensator, system is stable, which is good. Phase margin is close to desired, but the bandwidth is too small. So you see there is a little trade off here, right? If I increase the phase margin, the bandwidth goes down, and if I want to increase the bandwidth, the phase margin goes down. So I may have to go for a lead plus lag compensator under such scenarios. So as a rule of thumb, which may not be very proper justifications, we first design the lag compensator. So partially or partial compensation is via a lag compensator, and if we get the system to behave slightly better, then we can use the lead to overcome the deficiencies via the lag compensator. So here the bandwidth increases, phase margins are okay kind of thing. Then if it is like, say the desired is 50, this guy gives me 30, I can compensate this with the lead, and also the bandwidth can be increased, because the lead naturally has this tendency to increase the bandwidth of the system. Okay, so how do we do this? Okay, so we'll sorry. First thing we need to choose is what is the new crossover frequency. Okay, so I'll again go back to my plots. Okay, so I go back to my plot here, which is just the gain compensated system with k equal to 30, and I choose just by trial and error some partial compensation. Let me say I choose this frequency here where the phase is minus 145, which means the phase margin is about 35 degrees. And so when will this become the phase margin? When this frequency 3.52 is actually the gain crossover frequency. Okay, so I go here, So roughly about this point I want the magnitude to be 0. What is the magnitude here? It's about 16 dB. So this, the lag compensator should provide a negative gain here of minus 16.5, okay, such that this is the new gain crossover frequency. I am just assuming some partial thing here. You can also go to 150 and check. You can also go to minus 140 and check. So no hard and fast rule here. Okay, so what I need to do is compensate for this magnitude via the lag compensator, or in other words, I need to first design the beta. Okay. So how is the beta designed? Well, I am looking at now 20 log beta is about 16.4 in decibels. This means that log of beta is 0.82, and which essentially means beta is about 6.6. Let's assume that it is 7. Okay. Now I need to assume or find out what, or assume something for the corner frequencies. Let me just start by assuming T1 equal to 1. Okay, and with beta equal to 7, T1 equal to 1, my lag compensator, if I call it GC lag, would look something like this. I have S 1 plus j omega 1 plus 7 j omega. Okay. Now let's see what happens when I just plug in this compensator into my plant. Okay, I will call this as my GC lag. Okay, so something like this, and then I look at the Bode plot of the lag compensated system. So G is the gain adjusted, and then I have GC lag. Okay, so what is happening with this now? Okay, so I have now a phase margin of up to 22 degrees, it's fine, and I have a gain margin of 8.2, and well, let's check what is the bandwidth. The bandwidth is it's like pretty small, say about 4 point, say close to 4.3. Okay, now I have this lag compensated system which now has a phase margin of 22.5 and a bandwidth of about 4.5. Okay, now what I know now is that I could use the lead compensator to provide an additional lead here, and with the lead compensator my Bode plot also shifts to the right, so I could improve the phase margin and also improve the bandwidth. So first what I did is to partially compensate with the help of a lag compensator, and I will just do the lead part now. Okay, so how will we go about doing the lead part? Okay, step 2 would be design the lead part. Because this compensator had given me a phase margin of 22 together with a bandwidth of almost about 4.3 radians per second. Okay, so now the lead part. So what is that? Beta is fixed, okay, and alpha times beta is 1, so I know what is alpha now. So the phi of m, if I write it in terms of this beta, would be sine inverse of 1 minus, what is my alpha, is 1 over 7 by, there will be a bigger bracket here, 1 plus 1 by 7. This is comes out to be 48.6 degrees. Okay, now what will change is there should be another new crossover frequency. Okay. So, this new crossover frequency, now we have to adjust this into the lag compensated system, lag. Lag compensated with this one. So, this GC or G times GC lag, where G was the gain adjusted system with gain K being equal to 30. Okay, so once I know phi m, I also know alpha. I can compute alpha, or in this case I know beta, where alpha is 1 over beta. I can compute the new crossover frequency where the magnitude of the lag compensated system take this value minus 10 log beta. So this is minus 10, log of beta is 7. Log of beta is 7, this is minus 8.45, and this 8.45 occurs at omega m. I'll show you this from in the Bode plot, is about 6.15. Okay. Now once I get this omega m, so I know alpha or beta, I know omega m, I know phi m, I can compute T2 as square root of beta by omega m, and this turns out to be square root of 7 over 6.15. This is 0.43. Okay. So if you remember the formula, it was like 1 over alpha times T is equal to omega m square root of alpha. Just go back to the slides of the lead compensator and you will get to know this. Okay. So I am looking at this magnitude, this where the lag compensated system has a magnitude of minus 8.45, that will be the new crossover frequency, right. So that turns out to be 6.15, as we will see from the Bode plot of the lag compensated system. Okay. So where is it? Minus 8.45 is, yeah, roughly around here, right, 6.15, right. This is the frequency here, right. Okay. So now based on these things, I can write down how my lead part of the compensator would look like. So the lead compensator has now the form based on omega m is 6.15, beta being 7, T2 being 0.43. This T2 is essentially the time constant of or the numerator part of the lead compensator, at which we had here. So the unknowns in my design were T1, beta and T2. So now I am actually going to find out what is T2, and by doing all this process I get T2 to be 0.43, which gives my G lead, or if I call it GC lead, to be of the form 0.43s plus j omega plus 1 over 0.0614 j omega plus 1. Let us see how the overall compensation now looks like. So I have G, which was 30 over j omega, 0.2 j omega plus 1, 0.1 j omega plus 1. I had the GC lag, which looked like 1 plus j omega, 1 plus 7 j omega, and I have the lead. So let's see how my Bode plot has changed when I plug in this lead compensator. Okay, so my GC lead is 0.43 and a 1, 0.0614 and a 1, okay, something like this. So my overall compensated system with the lead and the lag compensator. I have G lag and I have a GC lead. Okay. Okay, so what are the characteristics now? First, okay, phase margin is 48.1. Let's look at how is the bandwidth doing. Well, bandwidth not doing too well. It's roughly about 8 radians per second. So with this, the phase margin is 48. The desired was 50. Was to be greater than or equal to 50, and the bandwidth is about 8 radians per second. Okay, again this bandwidth is for the open loop case. The closed loop bandwidth would roughly be about 11 radians per second, and we could check this by the Bode plot of the closed loop system, and the desired for us was 12. Now see the steps involved. So what did we do is, with the lag compensator we had some partial compensation where we had the closed loop, the gain compensated system with the lag compensator to be stable and a decent enough phase margin. We are still far away from what is desired and has some amount of bandwidth. Now I know that given this configuration I can now use a lead compensator to increase the bandwidth and also to push up the phase margin. So here the design involved choosing an appropriate beta, then I had to choose T1, and I was also taking this special case where alpha was 1 over beta. So given an alpha I had to choose a beta which satisfied this relation. So, and if you look at the design, what does the design give me? Well, I am close to the desired phase margin of 48, I am close to the desired bandwidth which is close to 12, here I am at 11. So what I could do is I could design the lead and lag component separately. Right, this essentially means choose an alpha which is not really depending on beta, or just fix the alpha what we had earlier. You can choose a different value of beta to be 9 or 10 or whatever, and then you can just come back to this. So what is required? So now we are close to the to meet the closed loop specifications. So what are required here are just little bit of tweaking of these values of alpha and beta so that we get to the exact values, not as close but really greater than 50 on the bandwidth about 12 radians per second. So I will not run you through that process. I will leave that to you as an exercise to play around with different values of alpha, or even designing the lead compensator completely separately. The aim of this lecture was to run you through that process of the design. Well, how to possibly use MATLAB appropriately, how to read the MATLAB plots, and so on. Okay. So to summarize, what we learned today was to design compensators in the frequency domain or across this module. In the 10th module, we will do something more, something little different. So these are not necessarily a part of a regular control curriculum, but these are important and interesting and also useful things to know. The first is experimental determination of a transfer function. So given a system for which I have no physical model essentially means I cannot realize them in terms of any circuit components or mechanical components. Can I just look at its frequency response, generate a Bode plot and get the transfer function? We will do the latter part of it. Given a Bode plot, can I generate a transfer function? And that leads to a very nice concept. What we should be careful of is that of non-minimum phase systems. So these are essentially the two things which we will deal in module 10. Might be a smaller module in terms of the length of the lectures than compared to the other modules, but still very informative and useful enough. Thank you.